welcome back. Today we're going to talk about mutually exclusive events. And before we get too far into the lesson, I'm going to just kind of let you know that the next lesson we'll be working on after this, which is on independent events, are often by students completely misunderstood and interchangeable with each other. Your brain is going to tell you that the two lessons are similar, and I'm going to try and convince you that they could not be more different, that these are actually drastically different ideas. Of course, this won't make a lot of sense until you see tomorrow's. I just want to get your brain going now to kind of get that understanding that what we're doing today is very different than what's going to happen tomorrow's lesson. So the good news is we've already kind of got an idea of what mutually exclusive means, even though we didn't call it that. Back in our last unit, we talked about disjoint sets in a Venn diagram situation, and that picture on the right kind of shows that. The idea of being mutually exclusive is the idea that two things cannot happen at the same time. Mutually exclusive means two things can never ever happen together. Specifically, you can't meet by both criteria at the same time. That's what it meant to be in disjoint sets. So for instance, in a deck of cards, drawing a single card that was both a club and a diamond, those are mutually exclusive events. They cannot occur together. And then there are events that can occur together, such as drawing a club and a face card. There are several ways that could happen. If you understood the idea of disjoint versus non-disjoint or joint sets, back when we were covering them in Venn diagrams in Unit 3, then that's basically the idea of mutually exclusion or mutually exclusive events. Now the equation that we use is actually going to be almost the same as it was back in that unit. The only difference is with mutually exclusive, when it comes to Venn diagrams, we talked about that equation. Specifically, the number of things in the union of A and B is equal to the number of things in A plus the number of things in B minus the number of things in the intersect. Meaning that you have to take out the number of things that are in both sets because they've been double counted. Now, if there's nothing in the intersection, there is no overlap whatsoever, that's what mutually exclusive or disjoint means, then we simplify down to that equation. The number of things in the union of A and B is the number of things in A plus the number of things in B. Now that equation's only true if there is no intersection, which is why I actually prefer the upper equation, because if the intersection is 0, then the top equation is the bottom equation. But if we start with the top equation every time, we're less likely to make mistakes. So that was what we saw in Unit 3. Now if we extend that to Unit 4 on probability, basically all I'm doing is taking those exact same equations that I had, and I'm dividing everything on both sides by the number of things in the universal set. And if I do that, instead of being the number of things in A union B equals the number of things in A plus the number of things in B minus the number of things in the intersect, I can say the probability of A union B is the probability of things in A plus the probability of being in B minus the probability of being in both. So the A or B is equal to A plus B minus A and B. Now, just to be clear about some examples of mutually exclusive versus non-mutually exclusive events, some things that are mutually exclusive would be rolling a die and getting an even roll or an odd roll. It's impossible to do those things at the same time, therefore mutually exclusive. If I roll a die and I'm looking at the probability of getting an even roll or a perfect squares being 1, 4, 9, etc. Well, 1 and 4 are the only ones we could get with a die. But those things are not mutually exclusive. It is possible to meet those criteria at the same time by rolling a 4. Similarly, drawing a card. Heart and spade, mutually exclusive. Heart face card, non-mutually exclusive, which we already discussed. Clothing. Wearing shoes and wearing boots. Under normal circumstances should be mutually exclusive, assuming you have 2 feet and, abide by normal footwear things. Non-mutually exclusive would be wearing shoes and wearing jeans. They can be worn at the same time. They don't have to be. There's no particular reason one would influence the other, but they can happen simultaneously. I do want to be clear that when we talk about mutually or non-mutually exclusive events, we're talking about two criteria for one action, not two separate actions. So for instance, when we go back to the card drawing example, I'm not talking about drawing a heart and then drawing a spade as two separate cards. I'm talking about drawing a single card, one action, and meeting or not meeting both criteria. That's the important factor here. We're not doing multiple events. We're doing one event, and we're checking it for multiple criteria. So let's jump into some examples and see how this actually works. Example 1, you roll a dice once. Okay, that's a good start, one action. What is the probability that either a 3 or 5 is rolled? Okay, first of all, we should decide, is this mutually exclusive or not? If I roll a 3, I obviously cannot roll a 5. If I roll a 5, I cannot roll a 3, not on the same roll anyway. And that makes these two things mutually exclusive. So, despite the fact that this notation might look a little bit weird, the probability of rolling a 3 union a 5, because again, our descriptions in here are just descriptive. We want to roll a 3 or a 5. This should equal the probability of rolling a 3 plus the probability of rolling a 5 minus the probability of rolling a 3 and a 5. Now, I put that one in despite the fact that we've already determined that these are mutually exclusive, just to show that it doesn't hurt to put it in. It just means that we acknowledge that that part is 0. So the probability of rolling a 3 is 1 in 6. The probability of rolling a 5 is 1 in 6. And the probability of rolling a 3 and a 5 is 0, because they cannot happen at the same time. And that equals 2/6, or if we wanted to write that as a percentage, and we do, it would be 33.3%. Now, what most of you should be thinking at this very moment is, why did we go through this? We could have easily figured this out like on day 1 of this unit. There are 2 ways to get the required things. We either want a 3 or 5. There are 6 possible rolls. We're done. And you're absolutely correct. On a test, if you jumped right to the 2/6 or the 33.3% is your answer, I'd have no problem with that one, because this one is pretty basic. The truth is, it becomes more complicated when things are not mutually exclusive, and students tend to always miss those. They tend to always miss them. So for number 2, let's take a look at this one and see if we see the difference. When rolling a single die, what is the probability that it will come up as either an even number or a number greater than 3? So over to the side here, I'm just going to write down even is going to be 2, 4, or 6. Greater than 3, that would be 4, 5, and 6. 3 is not greater than 3. 3 is equal to 3. And so even now, we could, I think, without too much trouble, see that the only numbers that meet our criteria are 4 or 6. Sorry, that would be ands. We're talking about ors. Probability of, now in this case, it's a little bit difficult to write out the explanation within that bracket of even or greater than 3. I guess I could do even or greater than 3. Now again, that's not supposed to be a mathematical statement, that's just a descriptive statement. So usually we don't have unions and greater than symbols in the same thing, but this is just a brief abbreviation. And that should be the probability of getting a even number plus the probability of getting greater than 3 minus the probability of even and greater than 3. So again, before we go too far, I think the answer is just going to be 4 out of 6, because the numbers 2, 4, 5, and 6, if we look over here, 2, 4, 5, and 6, those 4 numbers meet at least one of the criteria. Now the 4 and 6 meet both criteria, but 4 of them meet at least one, so it should be 4 out of 6. However, number of even, there are 3 numbers that are even out of 6. Probability of a number greater than 3 is also 3 out of 6. And then the probability of being even and greater than 3, that's a 4 or a 6, so 2 out of 6. And yeah, 3 plus 3 minus 2 is 4 out of 6, or 66.7%. Okay, could you have just done this one manually? Again, sure you could. You're more than welcome to. What you're going to find is that sometimes with larger problems, it becomes a little bit easier to use this notation. With easier problems, it's usually just better to do it by straightforward logic and kind of brute force. All right, question 3. A card is randomly drawn from a standard deck. What is the probability that the card is either a face card or a spade? So the probability of being a face card or a spade should equal the probability of being a face card plus the probability of being a spade minus the probability of being both. And this one we know is non-mutually exclusive. These things can happen at the same time. There are 3 cards that are face cards and spades. Now, I should point out that when we do these, sometimes there are simpler fractions that we could write. So for instance, the probability of being a face card is 3 out of 13. Each suit has 13 cards and 3 of them are face. The probability of being a spade is 1 in 4, because 1 out of every 4 cards is a spade. There are 4 suits. However, we're going to have to find a common denominator to add or subtract fractions anyway. So I'm going to think of the entire deck and say that the number of face cards is 12 out of 52. The number of spades is 13 out of 52. And the number of things that are both face cards and spades would be Jack, Queen, King of Spades. That's 3 out of 52. And so when all is said and done, we could put those together, and I think you get 22 out of 52. And if we want to write that as a percent, and again, we always do, 22 out of 52 is 42.3%. Okay, let's try one more. In a recent survey of university students, 85% consume alcohol at least once per week, 35% smoke cigarettes at least occasionally, and 25% do both. This is a bit of a misnomer. I think it's about 99.9% of students consume alcohol at least once a week, possibly per day, and 35% smoking cigarettes seems actually maybe a little high. But either way, we're going to assume that those are correct and that 25% do both of those things. What's a probability that a university student chosen at random smokes or drinks? Now we have to remember that smokes or drinks also includes students who do both. They've met at least one of the 2 criteria. If I said put up your hand if you smoke or drink, I think most people who've done both would put their hand up. I think that's just logical. So now I'm going to show you 2 ways we can approach this question. We can use the equation that we just been using so far. So the probability of alcohol or cigarettes, alcohol union cigarettes, is the probability of drinking alcohol plus the probability of smoking cigarettes minus the probability of drinking alcohol and smoking cigarettes. And again, you could choose different letters for those if you wanted. You could use D for drinking, S for smoking, whatever you want to do. Doesn't bother me any. But there we have it. Oh, my screen froze. Give me 1 sec. I got to bring it back because that line should have a few more letters in it. Okay, there we go. Now we're ending with the proper part, probability of alcohol and cigarettes. Okay, now the nice thing is we don't have to do these or calculate these probabilities. We already have the probabilities. Probability of alcohol is 85%. Probability of cigarettes is 35%. Probability of both is 25%. And so if I put those all together, I think I get out 95%. Okay. Sorry, my screen went weird again. 95% there. Now, I said there was going to be another way to solve this one, and it's actually going to be using a method that we've kind of already used. It's a Venn diagram. The difference being that we're going to put probabilities in instead of number of elements, but that's okay. So we have two overlapping circles because these are non-mutually exclusive events. They can happen simultaneously. Obviously they do, since 25% of students do both. So alcohol and cigarettes, 25% do both. So we'll put that in the middle, the intersection. 85 are in the alcohol bubble, but we have to remember that there's already 25% inside the alcohol circle, so we only need 60% more on the outside. So that means that 60% of students do drink alcohol but don't smoke cigarettes ever. And then on the other side, we have 35% that do alcohol and cigarettes. We already have 25 in there, so just 10 more. And if I add up the three of those, I get 65, 75, 85, 60, 70, 85, 95%, and there's 5% on the outside. So I could figure out that 95% by making a Venn diagram instead of using the equation. And again, on the test, unless the question prescribes what method to use or very specifically tells you what method that I want used, you're welcome to approach it however you'd like, as long as you show me something. Now, there are some questions that are obviously very short and pretty much are one line or one write down the answer type solutions. But in this case, either writing down what we wrote on the left with the equation or the Venn diagram on the right are both perfectly good, valid explanations on how you came up with your answer. All right, I'm going to let you try some mutually exclusive type homework problems. If you have problems with those, make me aware of them and I will do my best to assist you. Until next time, where we study the thing that you think will be like this but is not like this, have fun, and we'll see you later.